Hi ladies and gentlemen, today we're going to talk about the LU decomposition. We're going to look at Gaussian elimination, again executed through the way Strang is presenting it, which is elementary matrices. And these are just matrices, as we discussed before, which are executing elementary row operations. We provided all the background in elementary row operations last time. Now what we're going to do is we're going to expand that out to talk about how we can come up with our second decomposition. So recall our first decomposition, let me just jot it down quickly. We talked about writing A as C times R, where C is the set of linearly independent columns that make up A, and then R is a matrix which tells us how to combine those linearly independent columns to create all the columns that are in the matrix A. We have a similar type of a situation. Here we're going to have A equals LU. Similar from the standpoint that it's a decomposition, but it's completely unrelated in the way in which that decomposition is actually constructed. Let's take a look at the summary. So, as we saw in section 2.1, we can apply the elimination matrices to A and end up with a matrix that is upper triangular. So this isn't always possible. We are talking about matrices that are square. So when we do the LU decomposition, we are limiting ourselves to a square matrix, and that becomes important as we go through how this is actually done. But we did talk about this idea. And really the key for us is this piece of information here, where what we are going to do is we are going to take E times A is equal to U, and then the elementary row operations are invertible, which means that we can always do the reverse of them. If we take one row, multiply it times a constant, and subtract it from another, then the reverse of that operation is to take that and multiply by the constant and add it to the other. So every one of these elementary matrices has an inverse associated with it. And a large part of today's conversation is about the idea of inverses and a lot of the rules associated with inverses. So this is a little bit different, a little bit strange because it's buried here in section 2.2, but there's a big conversation associated with inverse matrices. So we really want to make sure that we're on the ball for inverse matrices, and I'll be highlighting those items for you. So let's talk just a little bit more about this. So let's say that we have E times A is equal to is equal to U, right? We've done this right here. We can left multiply, if E is invertible, we can left multiply by E inverse, and we will have E inverse times EA is equal to E inverse U, and any matrix times its inverse is the identity. And so what this is going to become then is just A is equal to E inverse U, since the E inverse times E is the identity matrix. And what we notice is that A equals LU and A equals E inverse U are the same thing, and the way in which we are going to define L is the inverse of the product of all of these elimination matrices. And there are a couple of items associated with the way this is constructed that makes it easy to do, which is why the LU decomposition is one of the more popular decompositions that we learn about. So where we're going to start then is taking a look at today's information and integrating what we talked about last time. So it says all the steps of elimination can be done with matrices. That's absolutely a true statement, but as we discussed last time, we would never do matrix multiplication in order to eliminate a matrix and make it into an upper triangular matrix. That is way too costly. So what we would do is what we discussed last time, which is Gaussian elimination on a row by row basis. And we'll talk more about that at a later date, but we would never do the procedure we're about to discuss in order to come up with the actual upper triangular matrix. We do it from the standpoint of creating this decomposition. So a little bit of review. You recall this system of equations we talked about a couple of lessons ago, and what I've done is I've turned it into a matrix vector form here, and then created the augmented matrix. And what we're going to do is we're going to take this augmented matrix and we're going to apply the elimination matrices. which is really the foundation for what we're talking about. So let me write down the first one. So this matrix here, right, when we think about taking this top row and sweeping it through the rows on the right-hand side here, we're going to take and just preserve the top row. And then for the second row of our output, we're going to take -2 times the first row and add it to the second row. And we're not going to take any contribution from the third row. And the reason we're doing that, of course, is we're going to take -2 times this number and add it to this one to create the 0 here. And that's the whole point of this elimination matrix, is to use the 2 as a pivot and create a 0 here. Remember from the previous video, we changed these pivots to leading ones. And Strang is not going to do that because in the LU decomposition, we don't actually do that part of Gaussian elimination. So he's just going to leave the pivots as the numbers that they appear to be on a natural basis. So let's take this product. I'll write it down for us. So we have the result of this first elimination step, which has created the all-important 0 here as part of our elimination. So remember, this matrix is what Strang is referring to as E21 for the elimination matrix. Now what we're going to do is we're going to again use the pivot, the 2, to eliminate the -2. And let me write in that elimination matrix. So in this case, again, thinking about this as sweeping through the rows, the first row we're going to preserve, the second row we're going to preserve, and the third row is going to be one copy of the first row added to one copy of the third row as we sweep through. So we know that's filling row 3 because that's the row that we have down here. And so that's going to give us the 0 in that product. Let me write the product down. And this is the matrix we end up with here. With respect to elimination, we really only have one step left, which is to use our second pivot, which in this case is a 1 right here, to eliminate the one that is below. So let me just make a quick note. This is the E31 matrix that Strang references. And now what we're going to do is we're going to include the last elimination matrix. I won't pause for this one. I'll just do it. We know we want to keep the first and second rows. And then what we need is we need -1 of the second row added to the third row. And the result here then, and let me write this down. All right, so this you remember from our discussion in section 2.1. It's exactly the same example. I wanted to break out the individual elimination matrices this time because the conversation we're having about the LU decomposition requires us to understand what each of these steps is going to do. What I'm going to do at this point is I am going to remove any of the color coding and just write down what we did. So we took the matrix A and then we multiplied by E21 on the left and then E31 on the left and then E32 on the left. So let me go back to the gray and write that down. We started with A, and then we did an E21 and then an E31 and then an E32. And it's not just the A matrix, but that's what we're going to talk about. In this case, we're actually solving a system, so we had an augmented matrix. But what I want to focus on is I want to focus on this A matrix right here and the resulting U matrix, which is down here. Right? So because we haven't done anything with respect to swapping columns or anything like that, then we can just track the progress of what's happening with the A matrix at each step. So this first 3 columns of the augmented matrix is always associated with A. And what that means is what we have here when we're only talking about A is U. This matrix here is the upper triangular matrix U. So what we need to do now in order to finish up our whole conversation about the LU decomposition is figure out how we can take the inverse of those matrices in order to create A equals E inverse U. That's the whole goal. That's the whole conversation for what we're doing. And we'll talk about the specifics of how we do this for our individual matrices here. But first things first, we want to talk about facts associated with the inverses. And again, it's a little bit strange that it's just jammed right here into section 2.2, but that's the way he has it set up, and we're going to go with it. So inverse matrices, first of all, we're always talking about a square matrix. Now, there is a conversation about pseudo-inverses, which we'll have later on in the course, but only briefly. We don't cover that section in the text, which is section 4.5. We're going to focus our inverse conversation on square matrices. So he talks about, okay, the matrix is invertible if we have a matrix, which we call A inverse, such that when we do left or right multiplication by that matrix, we get the identity. And that's called an inverse. And then he has lots of notes down here, and we're going to just briefly walk through these. This is a lot of the information associated with inverses. It's all kind of buried in here. So let me start before note 1. I'm going to actually start with note 0. And I will just switch over to the blue here. So note 0, which he hasn't listed, but he's said it. It's just important for us to keep in mind. A is square, right? This whole conversation about inverses only happens when A is square. The next thing with note 1, and the inverse exists if and only if the elimination produces n pivots. So A is n by n, that's our assumption. So A is square, A is n by n. And he says, and the word he leaves out here, which I think is important for us to understand, as long as we have n non-zero pivots. So what we need is, we need the pivots, and let me come back in here and identify the pivots for us. So these are the pivots. Unlike what we did with the Gaussian elimination, where we were doing it actual row by row operations, we did not turn these into leading ones. We left them as non-unitary numbers, which is fine. That's how you do LU decomposition. But those are still called the pivots, even though they're not called leading ones. And those pivots have to be non-zero. So that's what note 1 tells us. Moving on to note 2, then he's talking about the matrix A cannot have two different inverses. You don't need to worry about the proof for the demonstration here. Just understand if A has an inverse, that inverse is unique. Note 3, if A is invertible, then AX equals B has a unique solution. That's a really important result that we will leverage throughout the course. So the system has to be square. If the system is square and if A is invertible, then there exists a unique solution X such that X is equal to A inverse B. Note 4, suppose there is a non-zero vector X such that AX equals 0, then A has linearly dependent columns. So this one's a little bit bizarre. Let me add a comment here. So if AX equals 0 has a solution where X is not 0, then A inverse does not exist. Okay. A inverse does not exist, which means that A has linearly dependent columns. The term that we use here, we say A is singular. That is the vocabulary word associated with the fact that A inverse does not exist. So A is either invertible or it's singular. Those are the two options when A is square. Note 5 is a very important note. Let me highlight it here. A square matrix is invertible if and only if the columns are independent, linearly independent, which means if the columns are linearly independent, A inverse exists. If the columns are linearly dependent, A is singular. And vice versa. If A inverse exists, then I know the columns of A are linearly independent. And if A is singular, I know they're linearly dependent. And this really bounces back then to note 4. And then finally here in note 6, he provides what you may or may not have learned as the inverse of a 2 by 2 matrix. That's not really germane for us, but it's okay. It's there. It's not a problem. Continuing on then, let's take a look at note number 7. This is a little bit confusing. So what he says is, triangular matrix has an inverse provided no diagonal entries are 0. So if a matrix is triangular and the elements along the main diagonal are non-zero, then the matrix is invertible. Now, we must be very careful. He's done something that I think is a little bit confusing here. He makes it seem like A inverse is just taking the reciprocal of the elements along the diagonal. That is incorrect. So we will take the reciprocal of the elements along the diagonal. What is not being said explicitly here is these values are not the same. So he is just using that x as a placeholder for some non-zero value. It is not the same value. So when we do the inverse, the two blue items that I've circled are not the same value necessarily. They don't have to be the same. Then he goes through some exercises here, and then finally he leans on one of the more important properties of inverses, which is when we have a product and we have the inverse, it's the inverse of the matrices, but they are reversed in order. So AB inverse is equal to B inverse A inverse. A subtle item that is not provided a lot of attention here is the fact that, hey, if A inverse exists and B inverse exists, then AB inverse exists. So if I have two matrices that are invertible, their product is automatically invertible. Right? That's an important thing to think of also with the decompositions. So let's think for a minute. If A inverse exists, that means that L and U are both invertible, and vice versa. If L and U are both invertible, then we know that A is also invertible. And that's part of the information that goes here. And then finally on the bottom, he talks about the reverse order if we have a lot of matrices. So that feeds into the rest of the conversation about the LU decomposition. What we're going to talk about now is kind of the two items that make LU decomposition so accessible to us. What we want to do, think about what we're trying to do here to undo this product. What we need to do is first left multiply by the inverse of E32. Again, the inverse is not difficult. And let me just write it down. I need to multiply by E32 inverse. So I need the thing that is going to undo. Think about what E32 is doing. It's making the third row -1 copy of the second row and adding it to the third row. So the inverse of that is to take +1 copy of the second row and add it to the third row. So the inverse here is equal to 1, 0, 0, 0, 1, 0, 0, 1, 1. All I've done is change the -1 here into a +1. And we can verify that this is the identity matrix. Let's just do that quickly as a demonstration. Let me change to a different color and let me just throw down E32 here for a second. 0, 1, 0, 0, -1, 1. And then we can very quickly just see that, okay, I'm going to take the columns on the right-hand side there and sweep through. And I'm going to have 1 copy here. And then I'm going to have no copies of the first column, 1 of the second, -1 of the third. That's going to be a 0, 1, and then a 1 -1 in the bottom is 0. And then finally I take the last column. And we can see that we have the identity matrix. This green matrix is equal to the identity matrix. So the product is what we think it is. Be careful with the equal signs here. This is the inverse right here. Well, that means taking the inverses is really easy. I'm able to simply write down the following. I can write down and say, let me do it in red, A is equal to U multiplied times the inverse of 3, 2, which we already decided is 1, 0, 0, 0, 1, 0, 0, 1, 1. And then I need to take the next inverse coming in from the left-hand side, which is the inverse of E31. Again, I'm just going to change the sign. I'm going to change the sign of the piece that's not on the diagonal. So I have 1, 0, 0, and then I have 0, 1, 0, and I have -1, 0, 1. And then finally, I'm going to take the inverse of E21. Same thing, 1, 0, 0. Change the negative 2 to a positive 2, 2, 1, 0, 0, 0, 1. And what I have here is E21 inverse, E31 inverse, E32 inverse, all multiplied times U is equal to A. So that's the first thing that makes taking the inverses and building the L matrix so easy, is because it's very fast for me to find these inverses. No calculation required, really. When I first started this process, you look at the values here, 2, -1, and 1. If we come back up to where we originally did the calculations, I already knew what values I would use when I was doing this process. I knew I was going to use a -2 and a 1 and a -1, but I'm going to take the negative of those values. This is why Strang says we always think about LU decomposition as subtraction. So what I want is the negative of these values. So a 2, a -1, and a 1. And indeed, that's what I have down here, 2, a -1, and 1. The other really nice thing is, and we can demonstrate this to ourselves, but the product of, and we know this, we know that for the product of inverses, if I take these and put them together, what I'm going to end up with is, I'm going to end up with E21, E31, E32, and I'm going to end up with the inverse of that, but I need to write it in the correct order, right? Remember, when I take the inverse, I reverse the order. So this is really E32, E31, E21, inverse U. And that's equal to E inverse U. And remember, recall, this order is the same order as we were applying them here. So the product of all of these matrices, the inverse is right here. I just need to figure out how to multiply these together. That is awesome fact number 2. When I'm multiplying these matrices together, it turns out, and you can verify this for yourself, but it turns out that all I have to do is, and it makes sense to us, whatever row operation I did here, I could have done this row operation at the same time. And we did this when we did section 2.1. I can really do 1, 2, -1. I can use that one row and sweep through, right? I can grab that and I can sweep through with it in order to come up with my reduced form. So in this case, I'm rebuilding the U to get back to A. So it's the negative of the values I used. Then what I do is I just go over here and I put in the appropriate row from here, which is the second row. So I'm combining the first rows here and the second row here, and then my last row. And it turns out that this is exactly the correct matrix. This is E inverse. So I've used two things. The first one is it's very easy to find the individual inverses of these matrices, very easy. And then taking this product is very easy. I don't have to do matrix multiplication. I just fill in the spaces. So as long as I know what the actual elimination values are, and you can see this now, I know what values I was using for elimination as long as I think of elimination as subtraction. Those are the values that are going to go into my lower triangular matrix. I start with the identity and I put those values in and I have my lower triangular matrix, which means I'm never going to do matrix multiplication. What we're going to do instead is we're going to do what we talked about last lesson with the Gaussian elimination steps, and I'm just going to keep track of what the values are. I'm not going to make the pivots leading ones. I'm going to leave that part out. You saw that from last time. It's easy to just ignore that step and start using the value that's there to execute the elimination. So I leave that step out, and then for every value that I'm grabbing to do the elimination steps, that is the entry that I put into my L matrix. And that's all there is to it. So what I end up with then is I end up with A is equal to LU, where the L is built in exactly this manner where we use the pivots. He talks about that here. I wanted to show you what that was in a little more depth because I think his discussion here, it's okay, but I think it's a little bit short So I wanted to provide you with some information. So my recommendation is that you practice a few of these. It's relatively straightforward. And then, of course, thinking back to what we did in the previous lesson when we were solving systems of equations using Gaussian elimination, think about that systematic procedure that we said we could put into a loop without a whole lot of trouble, and think about what is the thing that you would grab out of that as a value for the L matrix. Because the U matrix is just going to come. As we do the Gaussian elimination, we're going to end up with a U matrix. All we need to do is keep track of the values for elimination to build our L. All right, so let's take a look at the questions for today. So here are the questions. And we're starting with several questions associated with the information about inverses, very important. Then we're going to take a look at an opportunity to practice some elimination matrices so you can think about how to build that L matrix. And then some discussion about invertible versus singular. So you work on those and we'll meet in class. Thanks.